Hello all, welcome to the next lecture of microwave engineering. So in the previous lectures we are discussing the characteristics of waveguides. Under this section we have covered what is mean by guide wavelength, and then we have covered what is the expression for phase constant, so which we got beta is equal to root mu epsilon into root of omega minus omega c square, omega square minus omega c square. And then we also covered what is mean by phase velocity and group velocity in the last lecture. So in this lecture, let us continue the other characteristics. So we are left out with two other important characteristics. So one is the wave impedance, and second is the attenuation factor alpha of the waveguide. Okay, so let us discuss these two concepts in this lecture. So firstly, let us start with the first parameter for this for today. That is the fourth parameter overall, which is the wave impedance or characteristic impedance of the waveguide. Wave impedance or characteristic impedance of the waveguide. Characteristic impedance of the waveguide. So this is the topic that we are going to discuss today. Right. So firstly, what is mean by wave impedance or what is mean by characteristic impedance? What is the definition? So in general, we represent this by a quantity called as ZZ. Okay. So the representation for this is ZZ. So if you are calculating it for TM mode, we write it as ZTM, and if it is for TE mode, we write it as ZTE. Okay. So in general, we express it as ZZ, right? For TM, ZTM, and for TE, ZTE. Okay, right. So what is this wave impedance? All right. So impedance, as we all know, it is the ratio of voltage to current, right? As per Ohm's law. So impedance means ratio of voltage to current. So here, in case of wave theory or field theory, so right, the impedance we generally express it as the ratio of electric field strength to magnetic field strength. Okay, so so here also the same definition. So the wave impedance or the characteristic impedance of the waveguide is basically the ratio of electric field strength in one direction to the magnetic field strength in the transverse direction, in the other transverse direction. Okay, so that is, you can also write this expression as this way. Okay, so it is the ratio of electric field in one transverse direction to the magnetic field in the other transverse direction. Okay, so that is a definition of wave impedance is, right, wave impedance is the ratio of, right, electric field strength in one transverse direction to the magnetic field strength in the other transverse direction. Okay, so in general case the transverse components are x and y, right? So ex by hy or ey by hx is generally what we refer as the wave impedance. We cannot take ex by hx or ey by hy. That is not correct. Okay, so we have to consider components in opposite transverse directions. Anyway, we won't get if e bar is present in x, h bar won't be present in x, right? So that is not possible. So therefore, always it is taken as the ratio of one transverse component to other transfer component. Okay, right. So this is the general definition of the wave impedance. Okay, the same thing we can also write in terms. We can also write it as a ratio of like this. So root of ex square plus ey square divided by root of hx square plus hy square. We can also express the ratio or the relation like this also. Okay, so this is correct, this is also correct, this is also correct, whatever it is. Okay, so the wave impedance is basically refers to the ratio of field strength, electric field strength in one transverse direction to the magnetic field strength in other transverse direction, that is ex by hy or hx by ey. Okay, right. Now let us calculate this wave impedance for the case of transverse magnetic and transverse electric cases. Okay, yeah, first for transverse magnetic case, TM mode. So what is the wave impedance in case of transverse magnetic wave? Okay, yeah. So for a transverse magnetic wave, right, we know that the components Which are the components that will exist? Transverse magnetic means Hz will be 0. So Hy will exist and Ex will exist. So I can write Ztm as ratio of minus ratio of Ex by Hy. Why does this minus come? Because of the orientations. Okay, right. So we can write it like this. Now we know that from the general analysis of the waveguide equations. Okay, so we know that this is nothing but minus gamma by ex can be written as minus gamma by h square into dou ez by dou x. Okay, so general formula for ex, I'm writing the general formula for ex, which is minus gamma by h square into dou ez by dou x minus j omega mu divided by h square into dou hz by dou y. Okay, whereas the expression for hy, what is the expression for hy? General expression, again same thing, minus gamma by h square into dou hz by dou y minus j omega. Okay, yeah, so minus j omega epsilon divided by h square into, right, what is the expression I get? Dou ez, sorry, dou ez by dou x. Okay, yeah, so this is the expression that I will get, right? So okay, so this is the formula, right, for hy, the general expression for hy. Now in case of transverse magnetic mode, we know that hz is equal to 0. Okay, so therefore, right, so substituting that here, ztm is equal to, so substituting hz is equal to 0, so this term vanishes, this term also vanishes, so what I get is gamma by h square. Okay, so yeah, sorry, yeah, gamma by h square into dou ez by dou x by j omega epsilon by h square into dou ez by dou x. Okay, yeah, so this dou ez by dou x and this dou ez by dou x gets cancelled, h square gets cancelled, so what I get is j omega epsilon by gamma, isn't it? Sorry, reverse. Yeah, so gamma by j omega epsilon. So this is what I get. Okay, right now, okay, so done. So ZTM is equal to, so one expression I got, ZTM is equal to gamma by j omega epsilon. Okay, yeah. So just a quick repetition. So as we discussed, wave impedance means ratio of right, electric field in one direction to the magnetic field in other transverse direction. So Ex by, here in this case it is written as Ex by Hy. So the general expression for Ex is this and the general expression for Hy is this. Okay, so in this, for the TM wave we know that Hz is equal to 0. So therefore ZTM is equal to, right, substituting Hz is equal to 0, I get like this. Okay, right, so in this h square gets cancelled, dou Ez by dou x and dou Ez by dou x gets cancelled, so these two terms cancel out. So ZTM is equal to gamma by j omega epsilon. This is what I get. Okay, so right, I will get ZTM is equal to gamma by j omega epsilon. Now from this, so we know that gamma is generally written as alpha plus j beta, isn't it? So right, because the wave is transmitting, wave is getting propagated, so my attenuation constant alpha will be 0. Okay, so if I write alpha is equal to 0, then what I get is gamma is equal to j beta. Okay, so let us substitute that here. ZTM is equal to, right, in place of gamma I write j beta divided by j omega mu. Okay, epsilon. So j gets cancelled, so this will become beta by omega epsilon. Okay, right, so this is the expression I got. Okay, so ZTM is equal to, so right, beta by omega into mu epsilon. So if beta value is given, omega value is given, epsilon is given, we can calculate the right expression for transverse magnetic wave impedance. Okay, so we can further, right, because sometimes, most of the times, we will be given with frequencies instead of right, betas, everything. So we can further modify this expression and get in terms of frequency. Okay, we can stop up to here also. No, it doesn't matter. So let us express the same thing in terms of frequencies. Okay, yeah. So in terms of frequencies, right? In terms of frequencies, so we know that beta is equal to root of mu epsilon into, right? What is that I get? Right? Root, yeah, root of mu epsilon into root of, okay, omega square minus omega c square. So this is the expression for phase constant that we calculated earlier. Okay, so right now substituting that here, ztm is equal to root of mu epsilon into root of omega square minus omega c square divided by omega into epsilon. Okay, right. So root of mu epsilon by epsilon square into root of omega square minus omega c square by omega square. Just modifying this, I'll get something like this. So this is equal to, right, this gets cancelled. So the first term will become root of mu by epsilon and the second term will become 1 minus omega c square by omega square. So this term, what is this term? Root of mu by epsilon, that is root of mu by epsilon. From our EM theory, we know that this term is nothing but the intrinsic impedance of the free space. Okay, the impedance of the free space or the intrinsic impedance, okay, of the free space, which is called as neta. Okay, so that is what, right, we get. So let us substitute that. So ZTM is equal to, therefore, right, this implies ZTM is equal to, right, neta into, okay, what I get, root of 1 minus omega c square by omega square. So this is the right expression that we get. Okay, so ZTM is equal to neta into root of 1 minus omega c square by omega square. Okay, so right, from this equation we can observe that, right, so neta value, right, neta is getting multiplied by some value which is always less than 1, isn't it? So omega c by omega square will be less than 1. Okay, so right, because omega will be more than omega c, that for the wave transmission to happen and the wave have to propagate, right? So whenever the wave is propagating, omega will be, that is the signal frequency will be, or wave frequency will be higher than omega c, cutoff frequency. So this value will be, right, always less than 1. So 1 minus something is, right, again 0 point, let's say something, okay, less than 1. So root of less than 1 will become much less than 1. So neta value, okay, is getting multiplied with a 0 point something, that is which is less than 1. So therefore this ZTM, okay, so ZTM in all cases will be less than neta. This is a very important conclusion we have to remember. Okay, so right, in case of transverse magnetic mode, the wave impedance will be less than the intrinsic impedance of the, right, waveguide or free space. Okay, and so whenever I have a parallel plane waveguide, and if this, in this parallel plane waveguide, if the EM wave is excited in transverse magnetic mode, right, then the wave propagation rate will be less when compared to the speed at which the wave, or the wave impedance will be less when compared to the impedance of the wave in the free space. Okay, so free space to bolchukunte, the impedance in the transverse magnetic mode will be less. Okay, that is a point we have to remember here. Okay, so right, so this is the case for transverse magnetic wave. So this is the expressions, right? So we can get a simple expression, ZTM is equal to beta by omega epsilon, or in terms of intrinsic impedance we can write it as ZTM is equal to neta into root of 1 minus omega c square by omega square. Okay, so right, this is the expression for intrinsic or wave impedance in the transverse magnetic mode. Okay, right. Let us calculate this intrinsic wave impedance or the wave characteristic impedance for transverse electric mode. Okay, yeah, let us do that also. Right. For the transverse electric mode, for the TE mode, transverse electric mode. So in case of this transverse electric mode, okay, right? So again, by definition, firstly, let us start with the definition. So by definition, ZZ, that is the wave impedance, here ZTE, is nothing but the ratio of, right, what is that electric field in one transverse direction to the magnetic field in other transverse direction. So here also we can write it as Ex by Hy, or also we can write it as Ey by Hx. Okay, whatever it is, right? Yeah. So we can take the either way, whichever way is convenient to us, we can follow it. It doesn't matter. So now let us go with the same way. So minus gamma by h square into dou Ez by dou x. Okay. Minus right, minus j omega mu divided by h square into dou hz by dou y. This is the expression for Ex, right, and the expression for Hy is given by minus omega gamma by h square into, right, the first term, which is dou, sorry, yeah, okay, minus gamma by h square into dou hz by dou y, right, plus j omega epsilon by h square into dou ez by dou x. Okay, so this is the terms that we get, right, okay, for Ex and Hy. Okay, right, now right, because this is a transverse electric mode, so let us substitute Ez is equal to 0 in this case. So therefore Zte is equal to, now substituting Ez is equal to 0, so right, Zte is equal to, this term will become 0 minus j omega mu by h square into dou hz by dou y divided by, so again this term will be as it is, right, dou hz by dou y, okay, plus 0. Okay, so this is the what I get. So I can remove the zeros. So 0 and a negative sign will be removed. Okay, h square gets cancelled. Dou hz by dou hz by dou y gets cancelled. So finally we will be left out with Zte is equal to, Zt is equal to, what is that I get? J omega mu divided by gamma square. Okay, J omega mu divided by gamma square. So this is the expression I will get. Okay, sorry, gamma, only gamma, not gamma square. Yeah, so gamma, j omega mu by gamma. Now again the same thing, gamma is equal to alpha plus j beta, right? Okay, so we can stop, right, this is also a valid right result. So okay, we can take that, but we can, let us go for the further analysis. So we know that gamma is equal to alpha plus j beta, but again since the wave is propagating, so alpha is equal to 0, so this implies gamma is equal to j beta. Okay, so let us substitute that here. Zt is equal to j omega mu divided by j beta. So j gets cancelled, omega mu by beta. So this is right, one expression for right, the wave impedance Zt. Okay, yeah, so simple thing. So wave impedance means ratio of electric field in one transverse direction to the magnetic field in other transverse direction. So here I get like this, and this is the general expression for Ex, this is the general expression for Hy. So in this case now I am putting Ez is equal to 0. So when I put Ez is equal to 0, I'll get something like this. So from this Zt is equal to j omega mu by gamma. Okay, yeah, so this is the thing. So gamma is nothing but alpha plus j beta. So alpha is equal to 0 and gamma is equal to j beta. Substituting this, okay, so we will get right, the term like this. Okay, so this is the expression for right, my right, transverse electric case. Okay, so that is a transverse electric case, right? Now from this again, as we did for the last time also, we can do this further. So Zt is equal to, substitute the value of beta. Okay, so omega mu divided by beta is nothing but root of, okay, mu epsilon into root of omega square minus omega c square. So this is equal to, so the mu divided by root mu, yeah, this will become root of mu by epsilon into 1 by root of 1 minus omega c square by omega square. Okay, so this is the expression I give. So Alright, I get like this. So Zt is equal to root of mu by epsilon into like this. So again, we can take, right, mu by root of mu by epsilon as neta. So therefore, Zt is equal to neta divided by, right, root of 1 minus omega c square divided by omega square. Okay. So this is the expression for, right, impedance, wave impedance of a, right, transverse electric wave. Okay, right. So we can see from here clearly that, right, 1 minus, because wave is propagating, that means omega will be more than omega c. Okay, since the wave propagation is happening, the wave frequency should be more than cutoff frequency, then only the wave can propagate, isn't it? So therefore omega is more than omega c. Okay, and because omega is more than omega c, that means this ratio will be less than 1. Okay, and all these things will be less than 1, right? So when I divide neta by something less than 1, right, something less than 1, then the ZTE value, right, will be more than neta. Okay, so, right, in case of transverse electric wave, right, the impedance of the waveguide will be more when, or the impedance seen by the wave inside the waveguide will be more when compared to the intrinsic impedance. Okay, so these are the 2 points we have to remember. Okay, so in case of transverse magnetic wave, right, the wave impedance will be less when compared to free space impedance. In case of transverse electric wave, transverse magnetic wave, wave impedance will be less when compared to intrinsic impedance. In case of transverse electric wave, right, wave impedance will be more when compared to the intrinsic impedance. So that is, right, the two conclusions we can get from this. Okay, so this is the concept related to the wave impedance of a waveguide. Okay, so simple. So firstly, and these expressions we have not derived it with respect to planar wave or rectangular waveguide. So they are general, right? As I told you, whatever the special characteristics we are discussing, all these are general. They are not related to rectangular, planar, or circular waveguides. Okay, so in each case, all of them is same. Okay, all the values are same, right? So okay, so right now, just a brief recap. A wave impedance means basically the ratio of voltage to current. Here in this case we take the ratio of electric field in one transverse direction to the magnetic field in the other transverse direction. So the expressions that we got, ZTM is equal to neta into root of 1 minus omega c square by omega square, and ZT is equal to neta by omega, right, 1 minus omega c square by omega square. So if I know the cutoff frequency, if I know the, right, wave frequency, the frequency of the wave, then I can calculate, right, their wave impedances. Okay, and the points we have to observe is, so ZTM will always be less than neta, ZTM will always be less than neta, and ZTE will be always greater than neta. Okay, right, so it will be equal to also. Okay, in that case it will become free space. Okay, right, this is the things related with the wave impedance. And in case of transverse electromagnetic wave, that is TEM wave, so we discussed that TEM is nothing but it is acting as a free space. So right, in here also the wave impedance in case of transverse electromagnetic wave is always equal to the intrinsic impedance. Okay, so it is same as that of the free space impedance. Okay, so we have to note this point. Okay, so this is the concept related to the wave impedance and the calculation of wave impedance in case of any waveguide. Okay, so the thing is, it is not related to either a particular planar or rectangular waveguide or circular. It is in general. Okay, right. So we will continue with the other parameter in the next.